Hi, I'm Greg Rosenthal, and I'm going to talk about bounds on the QAC0 complexity of approximating parity. QAC0 circuits are constant depth quantum circuits with arbitrary 1-qubit gates, pictured here as squares, and generalized Toffoli gates of arbitrary arity, which act on the standard basis by flipping the target qubit if and only if all of the control qubits are 1. More generally, we will consider QAC circuits, which may have arbitrary depth. QAC0 circuits are quantum analogs of AC0 circuits, meaning constant depth Boolean circuits with NOT gates and unbounded fan-in and OR gates. However, it is not actually trivial for QAC0 circuits to simulate AC0 circuits. This is because AC0 circuits are allowed fan-out for free, meaning at no cost they can create arbitrarily many copies of the input bits and of the outputs of gates, whereas QAC circuits are not granted this ability axiomatically. For QAC circuits to simulate this ability, we would like to compute the fan-out transformation on arbitrarily many qubits, which acts on the standard basis by flipping all of the target qubits if and only if the control qubit is 1. Then, by feeding ancilli initialized to 0 into the target qubits, we can create arbitrarily many copies of any classical bit. This does not violate the no-cloning theorem, because the bit being copied is 0 or 1 rather than an arbitrary qubit. This raises the question, is fan-out computable in QAC0? Preferably, we would like to compute n-qubit fan-out in size polynomial in n, but it is even unknown whether QAC0 circuits of arbitrary size can compute n-qubit fan-out when n is sufficiently large. The fan-out transformation is known to be equivalent, up to low complexity QAC reductions, to the unitary transformation corresponding to the parity function. Thus, the question of whether fan-out is in QAC0 is equivalent to the question of whether parity is in QAC0. And remember, we cannot directly simulate the usual exponential size AC0 circuit for parity in QAC0. For comparison, it is known that in classical AC0, exponential size is necessary as well as sufficient to compute parity. Finally, for added motivation, not only can QAC0 circuits with fan-out gates directly simulate AC0 circuits, but polynomial size QAC0 circuits with fan-out gates can also compute the majority function. Here is what is known about the QAC complexity of parity and fan-out. We're going to go through these tables line by line, first talking about the prior results for context, and then talking about the results proved in this paper. We define size and depth respectively as the number of multi-qubit gates and the number of layers of multi-qubit gates. Similarly to how in classical circuit complexity, it is customary to count only and OR gates toward size and depth and not count NOT gates. First, there is a trivial log depth linear size upper bound. This can be achieved for parity by directly simulating the usual NC1 circuit for parity. For fan-out, either reduce to parity or compute fan-out directly using cascading controlled NOT gates. Second, QAC circuits with sublinearly many ancilli require super-constant depth to compute parity or fan-out. More generally, there is a trade-off between ancilli and depth. Finally, depth to QAC circuits cannot compute parity or fan-out exactly when n is sufficiently large, regardless of the number of ancilli. In this paper, we do 4 things. First, we prove that constant depth QAC circuits can in fact approximate parity and fan-out arbitrarily well. For example, in depth 7, it takes exponential size. More generally, there is a size-depth trade-off similar to that of classical AC0 circuits computing parity. Here the parameter epsilon refers to the 2-norm error of the circuit on worst-case quantum inputs. We also prove a nearly matching lower bound for a certain subclass of QAC circuits that generalizes the circuit from our upper bound. This lower bound will be stated precisely later in this talk. Next, we prove that arbitrary QAC circuits of depth d and size at most 1/5 times n over d plus 1 cannot achieve much better than a 1/2 approximation of parity or Fanout, regardless of the number of ancilli. The definition of approximation used here will be given later in this talk and is such that it is trivial to achieve a 1/2 approximation. There is in fact a sharp phase change at about 0.23 times n over d plus 1 inherent to our proof. An interesting case of this lower bound is when d is theta of log n. Then we have an omega n over log n size lower bound, which nearly matches the previously mentioned O of n size upper bound. Finally, we improve the previously mentioned depth 2 lower bound to an approximation lower bound, where approximation here is defined the same way as in the previous lower bound. In the rest of this talk, we discuss proof techniques. All of our results are proved via reductions to the problem of constructing certain generalizations of the cat state. The cat state is the uniform superposition of the all zeros and all ones states on n qubits. It is named after Schrödinger's cat because you don't know whether the cat is alive or dead. More generally, we introduce a family of states named Nekomata after a two-tailed cat yokai from Japanese folklore. The states psi0 and psi1 here may be arbitrary states on an arbitrary number of qubits. Equivalently, Nekomata can be defined as states for which a standard basis measurement of some n qubits outputs the all zero string with probability 1/2 and the all one string with probability 1/2. So, why are these states interesting? In one direction, a circuit for Fanout can be used to construct the cat state via the well-known calculation shown here. The first equality holds by linearity, and the second equality holds by the definition of Fanout. In the other direction, given a circuit constructing a Nekomata, we can compute parity as follows. First, I will explain what each gate in this circuit means, and then I will explain why this circuit computes parity. First comes the circuit C, which by assumption constructs a Nekomata. Then comes a layer of controlled Z gates, each of which is a 2-qubit gate that acts on the standard basis by applying a phase of -1 to the 1-1 state and acting as the identity on the 0-0, 0-1, and 1-0 states. Next comes the conjugate transpose of C. After that comes an OR gate, which acts on the standard basis by flipping the target qubit at the bottom if and only if at least one of the control qubits is 1. This gate is easy to construct out of a generalized Toffoli gate and NOT gates using De Morgan's laws. Finally, the second half of this circuit is the same as the first half. So, why does this circuit compute parity? First, consider the case where X has even parity. The first layer of controlled Z gates has no effect on the Nekomata, so C conjugate transpose uncomputes the Nekomata back to the all zeros state, so the OR gate is not activated. Similarly, the second half of the circuit has no effect either. Now consider the case where X has odd parity. The first layer of controlled Z gates has the effect of flipping the sign of the component of the Nekomata corresponding to all ones in the first n qubits. This results in a state orthogonal to the Nekomata, so when we apply C conjugate transpose, we get a state orthogonal to C conjugate transpose Nekomata, i.e. orthogonal to the all zeros state, i.e. a superposition of standard basis states besides the all zeros state, so the OR gate is activated. Then the second half of the circuit uncomputes the state on the ancilli. Here's how we use this reduction. As described in the next two slides, there exists an exponentially large depth 2 QAC circuit that approximately constructs a Nekomata. Plugging this depth 2 circuit into the reduction from the previous slide gives a depth 11 circuit for approximating parity. With some further optimizations, we can decrease the depth from 11 to 7. Finally, we compute parity in higher depths by chaining together subcomputations of parity on smaller input sizes in a manner similar to the usual AC0 circuits for parity. In this slide, I will, among other things, precisely state the first of our previously mentioned lower bound results. Call a QAC circuit mostly classical if it consists of a layer of 1-qubit gates, followed by a layer of generalized Toffoli gates, followed by the conjugate transpose of that same layer of 1-qubit gates, followed by any number of layers of generalized Toffoli gates. We prove that in depth 2 and exponential size, a mostly classical circuit can approximately construct a Nekomata. And in sublogarithmic depth and not quite fully exponential size, no mostly classical circuit can construct much better than a 1/2 approximation of a Nekomata, regardless of the number of qubits. See the bottom of this slide for the definition of approximation used here, where C is a mostly classical circuit of the appropriate size and depth. Note, for comparison, that the empty circuit trivially achieves a 1/2 approximation. How are these results proved? Recall that Nekomata can be equivalently defined as states for which a standard basis measurement of some n qubits outputs the all-0 string with probability 1/2 and the all-1 string with probability 1/2. So I'm going to describe a procedure for sampling all zeros with probability 1/2 and all ones with probability 1/2, omitting some of the details of how QAC circuits can approximately simulate this procedure. Consider a grid with n rows and exponentially many columns. Each cell in this grid will hold 1 bit, or qubit. First, in each column, independently sample the all ones string with exponentially small probability and the all zeros string otherwise. Phrased in terms of quantum circuits, this entails constructing in each column the state indicated on the slide. This can be done with a single generalized Toffoli gate in each column, conjugated by 1-qubit gates. Then, in the second layer, compute the OR of each row. Why does this work? If we're careful about the constants implicit in the theta notation, then with probability 1/2, we will sample the all zeros string in every column, in which case the OR of each row will be 0. And with probability 1/2, we will sample all ones in at least one column, in which case the OR of each row will be 1. For the lower bound, we prove a concentration inequality for the Hamming weight of a standard basis measurement of any n qubits in a state constructed by a mostly classical circuit of low size and depth. This reduces to essentially a classical probability problem, because the quantumness in mostly classical circuits is only adjacent to the bottom layer and in a very controlled way. The main technical tool used here is a certain concentration inequality of Gavinsky, Levitt, Sachs, and Srinivasan. Now I'm going to say a few words about the other two main results in this paper and state them more precisely. First, consider QAC circuits of depth d and size at most 1/5 times n over d plus 1. After this slide, I will describe a normal form for QAC circuits. Once the circuit is put in this normal form, the proof basically consists of many applications of the triangle inequality. This gives a lower bound for constructing Nekomata, as stated precisely on the slide. This implies similar lower bounds for parity and Fanout as well, via the previously mentioned reduction from constructing the cat state to computing Fanout. Next, consider depth 2 QAC circuits. We kill off gates by measuring some of the ancilli in an appropriate product basis, and then apply the above theorem. This gives a lower bound for constructing the cat state, as stated precisely on the slide. Again, this implies similar lower bounds for parity and fanout as well. Finally, the aforementioned normal form for QAC circuits is as follows. For comparison, it is well known that in Boolean circuits, for simplicity, here's a formula, we can push all of the NOT gates to the bottom using De Morgan's laws, like this. We're going to do something similar for quantum circuits. Here is a QAC circuit with layers of 1-qubit gates labeled R, S, and T. First, insert something equivalent to the identity. Then, collapse consecutive layers of 1-qubit gates into a single layer of 1-qubit gates. Again, insert something equivalent to the identity. And again, collapse consecutive layers of 1-qubit gates into a single layer of 1-qubit gates. Now, this pair of 1-qubit gates cancels out, as does this pair of 1-qubit gates. Finally, group the gates like this. What we have is a layer of 1-qubit gates adjacent to the input, followed by a series of blocks, where each block is the conjugation of a generalized Toffoli gate by a layer of 1-qubit gates. What's nice about this normal form is that each block has a convenient eigendecomposition. Specifically, there is a single eigenvalue of -1, for which the corresponding eigenvector is a tensor product of 1-qubit states, and all of the other eigenvalues are 1. Thank you.